Okay, first thing we need to do here is list some perfect squares. If we take 1 and square it, we get 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on. If you take the square root of a perfect square, you get a nice whole number. Today we'll be looking for some patterns using perfect squares. As a child, you learned by experimenting with the natural world around you. What things did you learn by trial and error? Maybe that a fire is hot or an iron is hot, if you ever accidentally touched it or got too close. Riding a bike, you may have fallen off a couple times until you got the hang of it. Okay, so as a child, you achieved most of your learning from inductive reasoning. It's a process of observing data, recognizing patterns, and making generalizations about those patterns. Geometry is rooted in inductive reasoning. In ancient Egypt and Babylonia, geometry began when people developed procedures for measurement after much experience and observation. Assessors and surveyors used these procedures to calculate land areas and to reestablish the boundaries of agricultural fields after floods. Engineers used the procedures to build canals, reservoirs, and the Great Pyramids. No, too far. Throughout this course, you will use, and already have used, inductive reasoning. You will perform investigations, observe similarities and patterns, and make many discoveries that you can use to solve problems. Inductive reasoning guides scientists, investors, and business managers. All of these professionals use past experience to assess what is likely to happen in the future. When you use inductive reasoning to make a generalization, that generalization is called a conjecture. So considering the following example from science. A scientist dips a platinum wire into a solution containing salt, or sodium chloride, then passes the wire over a flame and observes that it produces an orange-yellow flame. She does this with many other solutions that contain salt, finding that they all produce an orange-yellow flame. If we were to make a conjecture based on our findings, we could say that salt makes an orange-yellow flame. That's just a generalization we have observed. In our first example, we're given the sequence 2, 4, 7, 11. Our first term here is 2, 4 is the second term, and there's a big hint. It says to look for patterns using addition, subtraction, multiplication, division, term numbers, or perfect squares. So if I look at some of the differences here, to go from 2 to 4, I'm adding 2. To go from 4 to 7, I'm adding 3. From 7 to 11, I'm adding 4. So I've added 2 to get the second term. I've added 3 to get the third term. So that means my next 3 terms, if I took 11 and add 5, I get 16. If I take 16 and add 6, I get 22. If I take 22 and add 7, I get 29. So if I want to describe this sequence accurately and completely in words, your hint says to state the first term and then explain how to find the rest. So here the first term is 2. The next term is found by adding the term number to the previous term. So when I'm looking for term 2, I had to add 2. When I'm looking for term 3, I had to add 3 to get it. Here's our next sequence. This is a very famous sequence called the Fibonacci sequence. So if you look to start, 1 plus 1 equals 2, 1 plus 2 equals 3. We just keep adding these consecutive terms to get the next one. So we add the last 2 numbers to get the next term. So if we took 8 and 13, we get 21. 21 and 13 is 34. 21 and 34 is 55. So we can say the first and second terms are 1. The next term is found by adding the 2 previous terms. Here's a sequence with some fractions now. Your hint is to rewrite with common denominators or find patterns for numerators and denominators separately. So if I rewrite these all with common denominators, instead of 0, we could say that's 0/8, then 1/8. 1/4 is really 2/8. Then we have 3/8, and 1/2 is really 4/8. So this helps us see a pattern. We're always just adding 1/8 to the previous term, or the numerator is going up by 1 each time. So your next three terms would be 5/8, 6/8, and 7/8, but we know we have to reduce those. Our pattern had fractions in lowest terms. So 5/8, 3/4, and 7/8. So we can say the first term is 0, the next term is found by adding 1/8 to the previous term and reducing. Okay, example 4, make sure you change. I think I fixed the typo in your notes. Your last term should be -27 there. So we have fractions and we have some whole numbers. So the big hint here is think about finding patterns for odd and even terms separately. For the odd numbers, we're just adding 1/7 each time. 1/7 to 2/7 to 3/7. For the even, we are really multiplying by -3. Okay, so then we're back at a fraction. That's 4/7. When we took -27 times -3, we got 81. And then when we added another seventh, we got 5/7 for the odd terms. So if we describe the sequence accurately and completely in words, the first two terms are 1/7 and -3. The next odd term is found by adding 1/7. The next even term is found by multiplying by -3.